Hi, welcome to the Unit Conversion and Dimensional Analysis slideshow. Unit conversion is an important skill for any scientist, and there are many ways to do it. You may have used moving the decimal point or memorizing which direction to multiply or divide. But in this lesson, we will use dimensional analysis to convert units. So what is dimensional analysis? It's a mathematical technique used to convert from your given value to the value you want to find. The given value is multiplied by something called conversion factors to get to your find value. So I like to think of dimensional analysis as sort of like a machine made of conversion factors, where you can put inside that machine your given and out will pop your find. So how does it work? The key to dimensional analysis is in the setup. You always start by writing your given over 1. And the reason why we write it over 1 is just to make it into a fraction. Then we're going to multiply our given fraction by our conversion factor. We want to make sure this conversion factor fraction is set up so that the units of the given are in opposite positions in the first and second fraction. So therefore, the part of your conversion factor that has a unit of your given will be in the denominator, since that's opposite to the numerator. This allows the units of the given to cancel out, leaving you with the units of your find. So the key with the setup is to make sure that the units that you want to cancel out are in opposite positions in separate fractions, one in the numerator and one in the denominator. So now I'm going to go into some examples to show you how to write conversion factors as statements, equations, and as a fraction. I'll also show you how to use conversion factors in dimensional analysis. So as it says in your notes, a conversion factor is a fraction made from proportional units that are multiplied with the given measurement to cancel out the units you don't want and keep the units you do. What exactly does that look like? Let's take a look at this example. The mass of a baseball is 149 grams. What is the mass of the baseball in kilograms? To answer that question, we would want to know how many grams are in a kilograms. We can express that in a statement by saying that there are 1,000 grams in 1 kilograms. So this is our unit conversion expressed as a statement. Because there are 1,000 grams in a kilograms, we can also express that as an equation by saying 1 kilogram is equivalent or equal to 1,000 grams. So this is a unit conversion factor expressed as an equation. But what does it look like in a fraction? In a fraction, we would take these two parts of the equation and we would set them up as a fraction. So we can take the 1 kilogram and put in the numerator and the 1,000 gram in the denominator, or vice versa, 1,000 gram in the numerator and 1 kilogram in the denominator. These are conversion factor fractions. The fraction that you use will depend on the direction of your conversion. Let's take a look at another example. The pressure on top of Mount Everest is 3,300 pascals. What is the pressure in atmospheres? Pascals and atmospheres are both units of pressure. To answer this question, we would want to know how many pascals are in an atmosphere. And the answer to that is that there are 101,325 pascals in one atmosphere. What would this look like as an equation and as fractions? So the equation would look something like this. 1 atmosphere is equal to 101,325 pascals. And as fractions, we could set it either as 1 atmosphere over 101,325 pascals, or vice versa, 101,325 pascals over 1 atmosphere. So now let's go into how do we set it up, how do we solve these? So remember, for dimensional analysis, we start with our given and we put it over 1. In this case, we're given 3,300 pascals. So we would put that over 1. The units are super important here, so you can't forget the units, because that's going to determine the setup of your conversion factor fraction. Now let's see if we can pick the right conversion factor fraction. Both of these fractions are an expression of the conversion factor to and from atmospheres in pascals. However, only one of them will allow us to convert from pascals to atmospheres. Can you guess, based on the information of the setup shown here, which one we would use, the top one or the bottom one. That's right, we would use the top one, because remember, we're trying to cancel out pascals. In order to cancel out pascals in the second fraction, pascals must be in the denominator. Again, the units that we want to cancel out must be opposite. So now that they've canceled out, the only unit we have left is atmosphere, which is our find. Now it's time to do the math. We're multiplying fractions, so when you multiply fractions, you want to multiply straight across. So that means we would multiply in our numerator 3,300 times 1, which is just 3,300. And in the denominator, we would multiply 1 times 101,325, which is 101,325. So then we would divide these two numbers, 3,300 and, this should be 3,300. There we go. So 3,300 divided by 101,325. And that will leave us with our final answer, which is 0.0326 atmosphere. Quick note, this is not in the correct number of significant figures, but I left it this way just so we can see the answer. Let's try another example. What is the diameter of a carbon atom in meters if its diameter in nanometers is 0.15 nanometers? So we would need to know how many nanometers are in a meter. There are 1 billion nanometers, or 1 times 10 to the 9 nanometers in 1 meter. What would this conversion factor look like as an equation and as fractions? The equation could be 1 meter is equal to 1 times 10 to the 9 nanometers. And again, there will be two fractions, 1 times 10 to the 9 nanometers over a meter, or 1 meter over 1 times 10 to the 9 nanometers. The one of these that we use will depend on our conversion. So let's look at the setup for this example. Our given is 0.15 nanometers, so we put that in the first fraction. Now, which conversion factor are we going to use? That's right, we're going to use the top one. Of course, I was kidding. We're definitely going to use the bottom one. Why would we use the bottom one? Well, take a look at the unit of our given. It's in nanometers. We want to make sure in that second fraction, nanometers is in the denominator so that nanometers can cancel out. So once we have it set up, we can just go ahead and multiply straight across. 0.15 times 1 is 0.15. And in the denominator, we have 1 times 10 to the 9, which is just 1 times 10 to the 9. And then we divide these two out, and we would get 1.5 times 10 to the negative 10 meters as our final answer. All right, let's look at one more example. And in this last example, we will see where we have to use more than one conversion factor. In this example, we want to know what's the diameter of the carbon atom in centimeters if its diameter in nanometers is 0.15 nanometers. So once again, we would want to know how many nanometers are in a centimeter. Now, with Google, you should be able to look this information up. But what if you didn't have Google and all you had was information about your base units, which is oftentimes what we have. And remember, when I say base units, I mean the units that do not have the prefixes like centi, kilo, milli, or nano in front of them. In this case, since we're measuring length using the metric system, the base unit is meters. We can convert, or we should be able to look up the information to convert from nanometers to meters, and also from meters to centimeters. So in this case, we're going to use two conversion factors, and we would want to know how many nanometers are in a meter and how many centimeters are in a meter. There are 1 times 10 to the 9 nanometers in 1 meter, and there are 100 centimeters in 1 meter. So this would lead to two equations that we would use, and then two sets of fractions. So let's look at the setup here with this example. For this example, remember, we have to convert from our given first to the base unit, and then from the base unit to the unit that we want to find. So in this case, we're going to go from nanometers to meters and from meters to centimeters. What would that setup look like? We'll start with our given, 0.15 nanometers. What's going to go in our first conversion factor? That's right, 1 meter over 1 times 10 to the 9 nanometers. What about the second conversion factor? After the nanometers cancel out, all we have left are meters, but we don't want to keep meters, we want to convert to centimeters. So what would that look like? That's right, 100 centimeters over 1 meter. And that way, the meters can cancel out. And then we can go ahead and do our math. So once again, remember, we multiply straight across. So 0.15 times 1 times 100 is in our numerator. And in the denominator, we're going to have 1 times 10 to the 9 times 1, which is just 1 times 10 to the 9. So what we would do in the end is multiply the top first and then divide by the bottom. And we would get 1.5 times 10 to the negative 8 centimeters. The last thing I want you to do is to rate yourself on a scale of 1 to 5. 1 means you're confused, and 5 is you can teach it to someone. Then describe what do you understand and what's confusing.